events, definitely feel free to let me know. Beyond the Seattle chapter, we also have a lot of sister chapters all over the world. So we are a very big family. So about the Women in Machine Learning and Data Science Group, we are a nonprofit organization. Our mission is to support and promote women and gender minorities who are practicing, studying, or simply interested in the fields of machine learning and data science. So we aim to create opportunities for members to engage in technical and professional conversations by hosting a variety of events, including Tech Talks, which is the one we are going to have tonight. We also have other events like workshops, networking events, and hackathons. Yeah, I will post this in the chat, so definitely follow up our Meetup page for future events. We also have a Twitter account, and if you have any questions, feel free to email us here. Yeah, so we also have a YouTube channel, and tonight's event will be recorded. And actually, let me show I hit on the record button. Will be recorded and posted on the YouTube later on.
I already started recording, so you're all set.
Okay, awesome. Thank you so much. I think, yeah. Okay, that's good. Okay, so next one. Yeah, so for tonight's event, we are going to have 3 tech talks from 3 amazing ladies, and Anna is going to be the first one. Skylar is the last one. So the first 2 talks are going to be live events. And the third talk is going to from Katinka. She's in Italy now, so she has recorded her video, and I will just play it, share my screen with you guys, and I will also share the YouTube link. So if the Zoom over YouTube quality is not great, you can always just watch it in your own computer. So every talk is about 20 minutes, and we are going to have 10 minutes in the end of each talk, so we can do Q&A. For this online event, so I will encourage everybody, since you guys are muted, like post your questions in the chat. And in the end of each talk, I will go through the questions and let the speakers answers to them. So for the third talk, the recorded talk, also feel free to post the questions in the chat, and we'll gather the questions and let Katinka respond to them in our event meetup page. Okay, so yeah, the original plans for this event to go live on YouTube, and but I have some trouble on doing with it, but I can try to do it again once the speakers start to talk. Okay. Okay, all right, yeah. Without further ado, let's kick off tonight's Tech Talks. So the first one will be Anna. I'm delighted to have Anna here. Anna completed a PhD in physics from UC Irvine in 2017, where she researched astroparticle physics. Afterwards, she moved to Seattle to work in data science. She is currently working at Vulkan on a team dedicated to improving climate models. So please join me in welcome Anna for talking about improving climate models with machine learning. Awesome. I will stop share screen and let you share the screen.
Thanks, Sophie. Also, yeah. I should mention, I should have written in there, I also worked at Zillow before I was at Vulkan. So
yeah,
part of the big Zillow crowd here.
I know, yeah.
Okay, is this full screen? I think it should be.
Yeah, it is.
Okay, great. Yeah, so hi everyone. I'm going to be talking about how our team at Vulkan is working on improving climate models with machine learning.
Nice.
So just a little bit of background about our team. So we're an open source philanthropic project of Vulkan Inc. here in Seattle. We sort of have 2 different working areas within climate science. So the first half of our team is people working to make climate models run, or sorry, not climate models, but working to make high resolution models run faster using a domain specific language and modern computing architectures. And then the second team that I'm on is trying to use machine learning to improve the accuracy of rainfall predictions in global climate models. Okay, so to give some background and motivation for our research, I'm showing a couple of figures here that are an ensemble of different climate models predictions for temperature and precipitation in the Pacific Northwest region over the next 55 years. So you can see that in this left figure here, while climate models are generally in very good agreement in predicting increasing temperatures in the coming decades and agree on regional scales generally, they have a much wider disagreement here on the right, you can see in their predictions of rainfall in a warming climate. So that's why the main goal of our team is to try and reduce this uncertainty in climate model predictions of future rainfall trends and extremes, because obviously these have a huge effect on society and people's lives. So a very obvious question to ask then is, why is there so much uncertainty in rainfall predictions as opposed to temperature? And the reason for this is, so I'm showing a little cartoon here of sort of how a climate model divides up the Earth. So we simulate climate into the future by dividing the atmosphere into a grid in both the horizontal and vertical directions. And then we evolve the atmospheric quantities like temperature and humidity within each grid box, time step by time step, using the equations of fluid dynamics and physics. This is really computationally intensive. And because you have to run a climate model for decades, because that's sort of the timescale that we're interested in order for a 50+ year-long simulation to run to completion in a reasonable amount of time and computational resources, we need to limit the resolution of these grids that we're running at. So a typical scale for a climate model might be a grid box that's like 100 by 100 kilometers on each side in the horizontal direction. However, as you can sort of see in this picture here, a lot of physical processes, like if you think about like clouds and stuff, if you look at the sky, they are described at much smaller scales than 100 by 100 kilometers, right? So for example, convection is really important for precipitation because that's a physical process that leads to thunderstorms and very heavy rainfall. And that is described at a scale of a few kilometers as opposed to 100. And sorry, I should also point out in this purple box here, this is sort of the movement that's being described by convection. It's sort of a more up and down in a column of air as opposed to side by side. So obviously a climate model can't directly simulate convection because its grid box is very low resolution. So instead they use what we call a parameterization in order to approximate the effect of convection leading to rainfall. And there are a lot of different ways to construct a parameterization and a lot of like hand tuning and different approaches. So there's a lot of differences between different groups parameterizations. And because this is responsible for a lot of rainfall, a lot of uncertainty in the precipitation forecasts. Okay, so I just mentioned that the convective processes that parameterizations are used to approximate are of order a few kilometers in scale. So there are simulations that actually can run at resolutions this high. For example, the ones that the other half of our team is working on are these high resolution simulations. So I'm showing an example here of like, this is the level of detail that these produce. And so these are sometimes called global storm resolving models or cloud resolving models because they can actually explicitly simulate the convection that's going on without having to resort to these parameterizations to approximate their effects. And these high resolution simulations typically do a much better job at predicting precipitation than the low resolution of climate models. But on the flip side, because they're so detailed, they're too computationally intense to run for decades. So like the goal of the sort of domain specific language half of our team is to get one of these able to run for like a few years. Like that's considered a long time for a fine resolution model. So the strategy that our machine learning team is pursuing in order to try and improve climate models predictions for rainfall is to use machine learning to augment a low resolution climate model and try and make it behave more like a high resolution model. But it's still going to be able to run at the lower computational cost of a low resolution climate model. Okay. So now I'm just going to talk a little bit about what goes into and what comes out of our model. So to construct our training data set, we use both a low resolution climate model and a high resolution simulation. And these are sort of run over the same time range. So for our prototype, we do just like 40 days, which obviously isn't a climate time scale, but is enough to sort of, try and test out different models. So at each time step, we save the state of the atmosphere from each model. So we have like the low resolution one that we're trying to improve. And then we have the high resolution one, which is sort of our target. And then we downsample the high resolution state to match the lower resolution. So this is sort of an example of what we're doing here. We're going to take our target, which is this really detailed thing, and then downsample it to sort of a blurrier looking data set. Okay. And then each column in the atmosphere, so remember back in this picture, this is sort of like one column of air at a point on Earth's surface. So each column is going to be one training sample. And then we have some vertical profile of like air temperature and humidity and some other quantities. So the inputs to the machine learning are the state of the column. So it's like temperature, humidity, maybe like angle of the sun at that time of day. And then whether the surface is land or sea. And then the outputs that we're going to try to predict are the changes to the temperature and humidity in that air column due to the effect of convection, okay, which again, we can't resolve that directly in this low resolution data. So again, just to reiterate, our goal is to make the low resolution model behave more like the high resolution data. So one kind of interesting thing about this particular problem is that the way we evaluate our machine learning skills, so what we call offline skills, like what you kind of traditionally do in machine learning, where you have some holdout test set, and then you measure the model skill just based on that holdout test set. But with the way we're saving our data, that really only measures how well this model does on a single time step of a climate model, which is like 15 minutes, right? So that's not necessarily that useful, and it doesn't really tell us about whether it's going to do well in future predictions, like years down the road. So the more important way of evaluating this is what we call the online evaluation. So that's when we take that machine learning model and actually plug it into a running climate model, so that each time step that machine learning prediction gets fed back into the model and influences the model on the next time step. So you can imagine that it's really easy to sort of get into a feedback loop if your model's not behaving well, where it sort of pushes the atmosphere into a crazy state. And that just makes the machine learning model make even crazier and crazier predictions, and then your simulation will crash. Okay, how am I doing on time? I'm at like 17 minutes. Okay.
I know.
Don't worry about the time.
Oh, that's time? Or
I just don't worry about the time. Yeah,
oh.
we have plenty of time. Yeah.
Okay. Yeah. So for this audience, since it's like a machine learning group, I think like maybe the most interesting things to go over are sort of the two different models that we've tested in this research. So our team actually uses both random forest and neural networks. And sort of when we use random forest, they work really well out of the box. So for example, like we don't really have to tweak hyperparameters that much at all to get a working, a model that works well in the online validation for random forests.